Good morning or good afternoon, wherever you are in the world. This is a very, very special occasion in the International Heat Transfer Conference of India, because for the first time, we are going to have Professor Arcot Ramachandran Endowment Lecture. Those who are in India or related to India know very well that Professor Arcot Ramachandran was the father of heat transfer studies in India. And instituting a lecture, endowment lecture in his memory is an appropriate step which Indian Society for Heat Transfer, Heat and Mass Transfer has taken. But I would say it's my great pleasure to chair this session because on one hand, it is in the memory of Professor Arcot Ramachandran. On the other hand, the lecture is given by someone who is a truly international leader in the area of heat and mass transfer, Professor Dimos Poulikakos, and a good friend of mine as well. Now, at the beginning, I will tell a few words about Professor Arcot Ramachandran, which won't be out of place here, because I think people attending this lecture should know things about him. Professor Arcot Ramachandran was born to a very illustrious family. In fact, his father was the longest serving Vice Chancellor of Madras University and Madras Medical College. And not only that, he was the chairman of the executive board of World Health Organization, WHO, and the first chairman of Indian Institute of Madras, Indian Institute of Technology, Madras, first chairman of the Board of Governors. Professor Arcot Ramachandran, though, took a different path. His father was a medical professional, but he took engineering. He studied in the Guindy Engineering College and left for Purdue University in 1945. And there, he worked with the two giants of heat transfer in the world of heat transfer, Professor Max Jacob and Professor George Hawkins. He worked with them. After that, although there were offers for him to stay back, he decided to come back to India. And he joined the Indian Institute of Sciences, Bangalore. And probably the first heat transfer lab was started in India under him at the Indian Institute of Sciences, Bangalore. He is the person who encouraged heat transfer studies in India, brought it to the curriculum of various universities and institutions. And in 1957, at the age of just 38 years, he became the departmental chair and dean of engineering of IISc Bangalore. And in 1967, at the age of just 44 years, Professor Arcot Ramachandran became the director of IIT Madras. Now, as the director of IIT Madras, he gave push to research. There are many stories about Professor Arcot Ramachandran which is heard even today in IIT Madras. One of them I would like to share, that one professor, associate professor appeared for an interview for promotion to professor, and he didn't get it. He was very aggrieved and he went to the director and he asked, "Sir, I am here for 25 years. I am teaching so much. How comes that I could not become a professor?" Professor Arcot Ramachandran walked, his office was in the 5th floor. So he walked to the window and called him. And he pointed out outside, said that banyan tree is there in this campus for 100 years. Shall I make it the professor? So that was Professor Arcot Ramachandran, who was very, very concerned about research and the quality of research. Now, Professor Ramachandran, after his stint at IIT Madras, in 1971, India started new Department of Science and Technology, and he was the first secretary of that, and probably the first secretary outside the bureaucratic community at the central government. And not only that, he also became the Director General of CSIR, the 40 national laboratories, the top man. So the story goes like in the morning, he used to go to ministry, and in the afternoon, he used to go to the CSIR directorate. Now, a visionary who changed India's science and technology in many ways. In 1977, he held a conference. Actually, UN held a conference in which he was chair. It was on science and technology for human development. And looking at his efficiency and his vision, United Nations wanted somebody to come as the human settlement, Under Secretary General for Human Settlement Habitat at Nairobi for Africa operations. So they asked India, naturally what happens, the politicians, they sent the name of a bureaucrat. But the UN Secretary General said that if it is to be from India, it has to be Professor Ramachandran. And then he was sent there and he did wonderful things. World Habitat Day was the brainchild of Professor Arcot Ramachandran. So wherever Professor Ramachandran went, he excelled, he showed new visions. Indian Society for Heat and Mass Transfer was founded by Professor Arcot Ramachandran. He was the founding president. But what is interesting, a couple of years back, about 15 years or maybe 15 to 20 years back, he himself said, look, I am no longer active. You are running the society. So I should not be the president anymore. He could have stayed president till his last day. But he decided to step down and hand it over to the next generation. This is Professor Arcot Ramachandran, who had the vision of the future. And as usual, from Shanti Swarup Bhatnagar Award to Padma Bhushan, which is the third highest civilian honor in India, he got all the awards. But awards cannot evaluate such a person. The person who brought not only the heat transfer education to India, but who brought a lot of sense in India's science and technology policy has been the Professor Arcot Ramachandran has been the architect for that. So with that, now I move to my second job, which is to introduce today's speaker, Professor Dimos Poulikakos. Professor Dimos Poulikakos is the founding director of Laboratory of Thermodynamics in Emerging Technologies of ETH Zurich. He was the VP Research of ETH Zurich from 2005 to 2007 and the ETH Director of the IBM ETH Banning-Rohrer Technology Center at the interface of basic research and future-oriented applications between 2008 and 2011. He served as the head of the Department of Mechanical and Process Engineering at ETH between 2011 and 2014, and of the ETH Energy Science Center, where from 2018 till now, he is the head of that center, and is a member of CORE, the advisory board for Swiss government on energy issues. He is also the president of Division 4 of the Swiss National Science Foundation, SNF. He and his group perform fundamental research in the area of interfacial and multiphase transport phenomena and thermodynamics across scales. So that means, micro, nano, or macro scales. And on the development of transformative technologies inspired by their findings. He works at the cross-section of thermofluids and materials. He got a lot of awards and recognitions, but major of them are the White House NSA Presidential Young Investigator Award in 1985, the Pi Tau Sigma Gold Medal in 1986, the SAE Ralph R. Teeter Award of the ASME, the University of Illinois Scholar Award of 1986, and the 2000 James Harry Potter Gold Medal of ASME. He was the Russell S. Springer Professor of Mechanical Engineering Department of the University of California, Berkeley, and the Hawkins Memorial Lecturer of Purdue University Now that there is a connection I could see. Professor Ramachandran, worked under Hawkins, and Professor Poulikakos was the Hawkins Memorial Lecturer. And he received the Heat Transfer Memorial Award of the ASME in 2003. And in 2008, he was a visiting fellow of the Oxford University and a distinguished visitor at the University of Tokyo. He is the recipient of the 2009 Nussel Reynolds Prize, awarded every 4 years. It's a very prestigious award of Germany. And then he is the, for his scientific contributions, he was given the 2012 Max Jacob Award. And everybody knows that that is probably the highest award in heat transfer worldwide recognized. And again, here is a connect. Professor Ramachandran did his PhD under Max Jacob, and Professor Poulikakos got the Max Jacob Award. And the other thing is that he was presented with the Outstanding Engineer Alumnus Award of the University of Colorado Boulder in 2012, and he received the habilitation of the National Technical University of Athens in 2006. In 2008, he was elected to the Swiss National Academy of Engineering. He is the president of Division 4 of the Swiss National Science Foundation. So this is only a brief sketch. I think with this, everybody is very eager to listen to Dimos, world-renowned heat transfer engineer and scientist, and a good friend of mine. Thank you, Dimos.
Thank you very much. Thank you very much for the invitation. Thank you very much, Professor Das, for the very kind introduction. Those a long list of events that you mentioned makes me feel very old, of course, right? So reminds me of my age, and it is an honor for me to basically be in the position to give the inaugural lecture in memory of Professor Ramachandran, whose outstanding contributions in science, technology, but also society we just heard from Professor Das. I picked a topic that is general for today's talk, and I'm going to share my screen if I can. All right, and that is the topic of condensation. Can you see my screen? Is the sharing good? Can you see my screen? Can you see my screen? And you can hear me well?
Yes, very much, very much.
So then effectively, what I chose today is the topic of condensation. It is a topic that affects society and technology, just like and science, just like Professor Ramachandran. And as you see from this sort of little graphic here, it is common in nature, of course, and many man-made applications in the industry, ranging from power generation, thermal power plants, or all kinds of industrial plants. Here we have an example of a chemical plant, water harvesting, but also more subtle applications where condensation plays a negative role, I would say, such as visibility through transparent surfaces, that is becoming more and more an issue as we actually going through this transition with pandemic and masking for some of us that wear eyewear, so to speak, glasses. Okay? So it is a very broad problem, and therefore, in today's talk, I will talk about the physics of it and how we learn from the physics to develop technologies that are very effective in water condensation. I have three aspects in my presentation. The first one deals with this broad area of power generation or an industrial condenser, so to speak. And that goal there is to maximize heat transfer during condensation. And the mode of heat transfer that allows to do that is is dropwise condensation. The second topic is completely different application. It is referring to this big problem that we have nowadays of, and we will have more into the future of water scarcity in the planet, so to speak, and then here we see how we can utilize the water in the atmosphere, harvest it, and then in that respect be able to combat this issue. And the last problem is one where condensation really is not wanted, but we have it whether we like it or not, and that is condensation on objects that we want them to be transparent. And then there I will show you how we develop technologies that ameliorate or avoid condensation. Okay. So then let's start with the first topic, with which we're all very familiar with in the general area of heat and mass transfer, is that of maximizing heat transfer and sustaining dropwise condensation. And I'm going to give some motivation for this, and that is, of course, this big area of power generation where condensation is very important. As you can see here, that still today in the lion's share of power generation, steam cycle is at the center of it, right? And of course, it is part of these activities that have the unwanted effect, of course, to generate actually large amounts of CO2 in the atmosphere, an effect that we want to mitigate and completely avoid. So condensation is very important in power generation because of the steam cycle, so to speak. And we want to then try to use our knowledge and optimize this process. And I show you here a typical power plant. This happens to be, I suppose, because of the cooling tower, nuclear power plant, where of course you have the turbine and so on and so forth, but the condenser is at the heart of this plant. I mean, you cannot operate without a condenser. I saw also a couple of pictures of industrial condensers, where you have surfaces. In this particular example, you have tubes that are conductive, upon which or inside which condensation can take place, and those surfaces are, as you can see already, they have a topography design, right? So improving the process of condensation can have a huge effect, actually, that as you see from this example, for a 900-watt lignite coal-based thermal power plant, where if you increase a little bit, like 1/10 the efficiency of the plant as a whole, okay, one can reduce the annual consumption of coal by almost 20,000 tons. So this is significant. And with condensation, the target is to basically try to improve by 1 or 2 or maybe 3% the performance by improving then the operation of industrial condensers. And the condensers come with certain requirements, of course, many of them. One very important one is that the surfaces we're dealing with are metallic surfaces. Yeah, so one can forget sort of PDMS or silicon surfaces we use in the laboratory and so on and so forth. And then, of course, the process has to be robust because they have to work reliably for a very long time. Now, what we are targeting here from the standpoint of condensation heat transfer is known to perhaps most of you in the audience, because condensation on the surfaces in this example can occur as a film. Now this film is moving downward and you don't even see it, or dropwise, and they that is, droplets are formed on the surface, and they, in a vertical configuration, are removed by gravity. In a flow configuration where steam flows on top of them, for example, it could be removed also by shear forces, but when they're removed, fresh surface is generated and the condensation is enhanced. So in that respect, this is a much more favorable effect than your film condensation, where the film adds the thermal resistance between the colder surface and the steam on the outside, and then of course that reduces performance. And the effects that we're looking at are those of hydrophilicity. As you see, a droplet spreads nicely on on a surface, and then eventually, if the droplets spread, eventually they will generate some kind of a film, right? This theta angle is small then for philic surfaces, and then the other extreme is where these droplets the surface, so to speak, is more phobic to water, and the droplets tend to bead up, or the theta is larger than 90 degrees. You can go to the other extreme, 180 degrees, where the contact point theoretically would be only 1 point. That is also unwanted, so to speak, because if the droplets do not touch the surface, then we will have no condensation, so to speak. So the question is of how do you reach a happy medium in between while having sustainable dropwise condensation. So the issue of hydrophobicity and perhaps superhydrophobicity is very relevant. Surfaces that cause hydrophobicity, and in particular superhydrophobicity, are not smooth surfaces, are rough surfaces, as you see that. They became very popular about 10 to 20 years ago when they were observed, of course, on plants, like this is the famous lotus leaf plant that shows superhydrophobic behavior. And as you can see from the simple system of a droplet that I show here, for superhydrophobic surfaces, this angle theta, the contact angle, is much larger than 90 degrees. 0 would be a film, and 180 degrees would be like a boiling ball on a hard surface, so to speak, which you also do not want. And they work as rough surfaces in technology and, of course, in nature, because a roughness allows, as I show here, the droplet to sit on top of it and allows the appearance of the intervening air layer, or whatever layer you want, gas layer under it, that supports the droplet, and then it reduces contact, and that improves the mobility of the droplet. And one can do that with one level roughness or multi-level roughness, a hierarchic effect, so to speak, okay? As you see in this cartoon down here, you can go 2, 3, 4, whatever you want level roughness. Usually 2 will suffice, so to speak. And you see that also in nature, where you have on the lotus leaf, you have a first level roughness. And then on top of this, if I expand this here from 10 to 2, I see the structure of these bumps. And there you see a second level roughness that is responsible for the superhydrophobic behavior of your leaf. And the question is, how about chemistry? All right. So, well, if those surfaces happen to be surfaces with very low surface energy, then they will probably work by themselves. So that rarely happens because the materials we use in applications are not so, and that will require some chemistry on top of it. Usually monolayers of various chemicals. A typical one is silane or various other things. And the other challenge is, of course, is the robustness of these monolayers and of this chemical treatment. Therefore, people have been also working very hard to generate to improve the robustness in particular of such treatments, going with processes like initiated chemical vapor deposition and so on and so forth. So that is one aspect. And of course, nature does it very well for its functionality. As you can see here, it's a beautiful, on this plant, superhydrophobic behavior based on this sort of two-level roughness. You see like an arm, a micro arm, you know, and on top of this, you see maybe I call those fingers, and then of course the droplet sits at the tips, at the fingertips of this structure here. But of course, then that shows you at the same time the fragility, this fragile structures. Also the fact that, of course, even if they're not fragile, pressure can push the droplet through these structures, impale it, and the functionality is lost. So there are a lot of challenges in going from an inspiration that you see in nature that works well for the application in nature to an engineering problem where you need, we have a lot more stringent requirements. And that is, of course, the challenge of the entire thing. So then, basically, what we want is to maintain a desirable phobicity. We want these droplets to roll, and for that you need to have a superhydrophobic surface. Now, what is a superhydrophobic surface? That is, of course, also roughly defined. Let's say here that this angle should be about 150 degrees. maybe 160 degrees. And then, if you tilt it and you have a difference between the receding and the advancing contact angle, that should be relatively easily done, let's say below 10 to 15 degrees. If those two criteria applied are valid together, then of course you have a surface that basically gets rid of the water easily. You can call it superhydrophobic. We need, of course, scalability, we need robustness, and we need metals for the first part of my talk. And therefore, I will discuss to you two strategies on how to create structures like that on metals. One is simply machining, all right? I call it machining. And the second is wet chemical etching, but both of them come, of course, with a rationale, with an engineering thinking as to what you get out of the surface to get the superhydrophobic behavior that you need. And when it comes to machining, an interesting concept is one that makes a surface that has cavities like the one that I show here, and it is hydrophobic or superhydrophobic, so that when vapor generates, and unlike classical superhydrophobic behavior where you have water sitting on top of those structures, in condensation, water nucleation tends to take place at the bottom of this cavity. So it's a lot more challenging, right, to basically deal with when you condense. And then, of course, it keeps growing, and you really want to have the structures, design the structures rationally. So you have a behavior like this, where as the droplet grows, there is a capillary pressure difference within the droplet because of the different curvatures that are imposed by those reentrant cavities that are designed on the surface in the roughness, so that as it keeps growing, then of course this becomes bigger and pushes the droplet out. And at the end, you might have a situation where you have this being pushed out all by itself, but it could be helped by coalescence by another droplet in the surrounding. So if there is if there is an event like this, the smaller droplet will empty itself in the bigger droplet because of the so-called Ostwald ripening effect. And then, of course, with that, the water will move out of the cavity. So we look, of course, into many ways of how to texture the surfaces. You can do nanotextures, as you can see here. This is a chemically obtained nanotexture with chemical etching, okay, in aluminum, or with boiling. You can simply boil aluminum, you generate structures like this. Of course, you have to have a protocol for this. You can machine grooves on this. You can generate these previous reentrant structures that I discussed that will help droplets move out of the structure with a laser machining, or you can do the same, and that's very challenging, okay, the same, or it's less challenging, but easier to upscale, all right, to do the same, achieve this effect by some kind of a chemical etching that when you look at it all together, it does provide the surface with this kind of an effect that I discussed earlier. And the surfaces have to be treated chemically at the end of the day. That is the last layer, the last sort of part of the process to make them super hydrophobic. So we worked on this, and in particular, my old PhD student and postdoc, and now your assistant professors at IIT Ropar, Chandrasekhar Sharma, worked extensively on this, and he showed a very nice process, easily upscalable, where you could create this kind of a structure that has this reentrant sort of nature. It consists of larger cavities that are decorated. Look at this. This is 20 microns. That is 2 microns with a nanostructure, and working collaboratively, these structures do what I told you earlier. I'm going to skip this. Well, why not? Okay. And they're able to basically move the droplets out and generate a relatively early departure. And you do want early departure because you see that we have an experiment here on a surface like this. Sorry. Okay. Doesn't seem to want to play. Okay. Here we are. So you have these droplets that are created on the structure, and they keep growing and they keep coalescing, and they're all moving up. You see, they're ready to be swept off or roll off, right? And you do want early departure because it is for small droplets. I mean, the droplet growth is an exponent that is less than 1, and the early departure is where effectively the droplet growth is more effective heat transfer Y. And we have the mechanism here. Chandra went ahead and did this beautiful graph that shows the mechanism. You see these droplets growing in here. And initially, of course, the capillary pressure would be not favorable, but as they grow, you keep growing the outside. This is going to be favorable to expel. And at the same time, one might have contact with outside droplets. So the droplets get out, and if by coalescence there is enough energy, then they can even jump away from the surface, right? So you can see here videos showing this effect. So you have a droplet at this point, and another droplet growing there, and another droplet growing from a cavity. It touches the previous droplet, and 1 and 2 pop out of the surface. You could even do the same by having them jumping out of the surface, and so on and so forth. I have a second video here, which I will skip for brevity. You can do the same, of course, with nicely organized, regularly structured surface, which are done by a laser, followed by chemical treatment, as you see here, and then you see the same effect that I described earlier, where they grow from the cavities. Those are well-organized cavities, of course, and you see how they coalesce and keep coalescing. Then the entire thing would be out and fall off either by gravity or by an incoming stream of steam. So they work very well. And here's an example of what they do to heat transfer, because you see we do a lot of work on droplet. You can see published on generation, condensation like that, but you rarely see, heat transfer coefficients. So the visuals are beautiful, and we stop at the visual, but unless we measure heat transfer coefficients, we haven't done the job. So Chandra and his co-workers here went ahead and looked into careful experiments on the heat transfer coefficient, and you can see now the effect using this example surfaces here in this presentation. I chose the regular hierarchical texture, and you see how you can increase tremendously the heat transfer coefficient. I compare with the hydrophilic surface, let's say copper or aluminum surface with no structure and philic, and then our best you can do, so to speak, in that study, at least hierarchical hydrophobic surface. Compare the two, you have a 700% increase in the heat transfer coefficient. So that could be a successful way to go, provided, of course, that the surface is robust. And we've done some robust experiments here, very challenging experiments. We have a setup in the lab where effectively we test the surfaces with hot steam at high velocities, much more challenging conditions than the real applications in industrial condensers, where you don't have that at all. You don't have any high velocities, and you have a vacuum. Okay, so if you have a vacuum, a significant vacuum, then of course it's a lot less challenging for the surfaces. But we cannot sit there for years and do it. It's very difficult. It's doable, very difficult to do the real time experiments. So therefore, do accelerated experiments with a lot more challenging conditions. So you see here that we started with superheated steam at 111 degrees with a velocity of 3 meters per second on the surface. And you do have clearly a dropwise condensation. You don't transition to film. That goes up to 11 days. After this point, we switch to 9 meters per second, a very challenging condition. And you can go for 11 days, almost 2 weeks, so to speak, maintaining the hydrophobic dropwise condensation behavior and the heat transfer coefficient. So that's sort of a rewarding result. Now, I'm going to close this first part of my talk with going to a different kind of a surface. Okay, those are not anymore rough surfaces. Those are liquid-infused surfaces. So this is another approach where the contact angles of the contact angle of the condensate, so to speak, the droplet does not have to be very large, but the droplet's extremely slippery. So those are liquid-infused surfaces, and usually they're done by sort of imagine a very thin deposited or roughness or carpet, so to speak, on the surface that is infused by the liquid, all right, and the condensation occurs on top of it. So since it is infused by the liquid, there's very little friction and the droplet slides on the surface. So a bit of a different approach. And there is a lot of work that's being done on this. And our contribution to this is the following. A big disadvantage, in addition to the fact that you have to infuse them with a liquid that is a non-miscible liquid, a lubricant, non-miscible with water, obviously, and so on and so forth. And there's issues with that. These layers are insulating because the liquids, the liquids that are used as lubricants are not very conductive, as you cannot avoid that. They're usually of low thermal conductivity. And the same is true with many of those porous structures that are generated on the surface, all right? So therefore, we try to do this with a very conductive structure, and we're able to grow. That's the work led by my other postdoc currently, Abhinas Tripathi. He grew extremely thin layers of graphene that sort of look as a cartoon like this, all right? And they are porous as a whole, about 70 nanometers thick, all right? And then impregnated those with a lubricant. And the huge advantage of this is that it is sort of, so to speak, a new record in having a low thermal resistance, because first, the graphene is a lot more conductive than most materials. State-of-the-art surfaces of this kind are represented by copper oxide, and there the oxide layer is thick, about 2 microns, all right, and the oxide conductivity is a lot less than that of vertical graphene, all right. And second, of course, the simple thickness. The thicker it is, the more the thermal conductivity. And he was able to, in particular, the second effect is really detrimental. I mean, unexpectedly detrimental, because you say a micron or two, what harm can it do? It can do a lot of harm, all right? And as you can see in the second slide, that is another view of a copper substrate with a vertical graphene on top of it, about 70 nanometers. And this is a typical lubricant that you see. You see the conductivity of the lubricant is kind of unavoidably small, but there is a huge difference between our surface with that vertical graphene and the copper oxide, which would be the state-of-the-art surface with which we are competing, right? And the resultant thermal resistances, and there is an interesting study on that within the same sort of publication, is significant, The 2 micron copper oxide, because that is what it is, you cannot go much smaller than that, all right? Copper oxide, the liquid-infused surface, has a much larger thermal resistance than our 70 nanometer vertical graphene liquid-infused surface by an order of magnitude. And that makes our surface a lot more favorable heat transfer-wise. As you see from these results of heat transfer coefficient versus subcooling, where effectively the state-of-the-art liquid-infused surface behaves like so, like I see here. This is the red. Even the pure copper oxide without the least aspect of it behaves a little better. And our surface, of course, is significantly more effective regarding heat transfer. Because of its conductive nature, but most important, because of this of its thickness. Right? So that's an interesting other way to go about increasing heat transfer in condensation. You should always think about robustness as much as you can, and then you see how this surface operates with time. And the behavior you see after cumulative 3 hours up to 25.5 hours that we run the experiments is very good. The surface maintains dropwise condensation. So with that, I hope I gave you a flavor on some work that we do today, and it's done also by other groups worldwide in the area of dropwise condensation with an eye of maximizing heat transfer. And then I'm going to move to the second topic, again condensation, but now the focus will be atmospheric water harvesting. And it's easy, of course, if you have a surface in the evening, you put it out, dew will form on it, because of course in the evening the temperature of the surface will be lower than the saturation temperature, and then effectively you have dew formation. And a lot of methods rely on this when it comes to atmospheric water, but in our case, we'll show you how you can do that continuously, also when the sun shines on your surface. Right? So then I'm moving into this, all right, and I'm going to give you a little bit of motivation. It is about then global water stress. Okay, it is a real problem. If you look into today's situation, baseline water stress, the red regions is where you really need to have more water. And if you can see here, many parts of the world are so, and India, of course, belongs into that category. The gray here is areas with low water, but also arid, but also very low water use because you have deserts and so on and so forth. But it is the red areas that are in need, and they keep increasing as you look into the future. Right? So then people have been looking into many ways of how to gain water. I mean, there are industrial desalination processes that I don't need to remind you this. All right. But you see, if you look at water per se, 0.5% of water of the Earth's water, if you count everything, of course, is available for human consumption. And 40% of the world population is affected by water scarcity, right now, right? And if you look into the future, the situation looks like this. There's a lot more red, which is, if you look at the ratio of withdrawal to supply of water, the situation will be a lot more acute. And in many regions of the world, including India, that is basically is hosting my presentation today. So therefore, I chose this topic because I thought it might be also interest you. Now, try anything you can. Okay, it is about a cocktail of solutions, so to speak. But the atmosphere could be a part of it. All right. Part of the solution, because the water available in the atmosphere is about 3 times the yearly global water population. So there's quite a bit of water there. So we can add this to our, let's say, quilt of solutions to basically fight water scarcity. And then what I'm going to bring into the forefront here is the concept of radiative cooling. Okay. And I'm going to come into this so-called infrared atmospheric window, which became very popular in the past, I want to say, 5, 7, 8 years, since there was the group of FAN at Stanford that did a paper where they showed that there is this window, which it was there, but not many of us were aware of it. If you look at the transmittance versus wavelength, okay, in the atmosphere, there is this window, all right, between 8 to 13 microns, where this transmittance is very high. Right? Now it is in the infrared, right? So, and the reason why this window is very important is that there, if you emit, all right, there's no absorption in the atmosphere. All right, the transmittance of the atmosphere is very high. And basically, you communicate radiatively with the outer space, right? So effectively, if there were no other effects like convection and so on and so forth, at equilibrium, if you had vacuum in between, you would reach the space temperature within that window. This window is limited on one side because of water absorption, because the presence of water in the atmosphere is absorbing a lot of radiated heat of the atmosphere, and on the other side, mainly because of CO2. Right? So effectively, there is this window, and we can rate if we could design our surfaces so that they radiate energy through that window. Then, of course, they could be cooled because the atmosphere allows that. Right? If you have an emissive surface that emits very well, that surface would absorb also very well in the same wavelength range, all right? But since in that window there is nothing to, the atmosphere itself does not emit, there's nothing to absorb. So this window is a window of escape of thermal energy of the Earth toward the outer space. So the challenge is now to generate surfaces that would then emit in that particular window. And that's what we did. And that's our device. Of course, a picture of a device, and I see a lot of papers. People send me papers I act as an editor, and they have like 10 photographs in the paper. Don't send me, maybe one photograph is enough, because this photograph looks nice, but it doesn't tell me much quantitatively, as much as a nice diagram like this, because then the concept is that I make a device, okay, and this device is not a very simple device, although it looks very simple, and it is, but it is very affordable, and you can make it rather easily, right? But scientifically, is not a very simple device. So this device is for cooling, but also for condensation, right? So it consists of a selective emitter that I told you before that has to emit through that window, all right? It has to, of course, at the same time, avoid everything else, reflect, that is, because if I want to use during the day and the sun shines upon the device, I want to get rid of all that, you know. It should reflect the sunlight within outside this window. And of course, you know, because there is this, the radiation is rather complex, okay? There is angular, not only wavelength dependency, but also angular dependencies. And of course, there is conduction and convection in the atmosphere. A radiation shield is needed to ameliorate all these effects, all right? There is an insulated film here to ameliorate convection from the atmosphere, and also ameliorate direct condensation on the surface. And there's a condenser on the other side of this, all right, where this surface gets cold, even during the day, even if the temperature during the day outside is high, okay, this will be cold and will generate condensation, right? So how do you do all that, all right? So the first thing I want to discuss of the three parts, you have to design separately, of course, the radiation shield, which is an very important aspect of this. People miss a lot of times. You have to design the selective emitter, all right, and then you design the condenser separately. Okay, so a few words on the selective emitter. That is actually not that difficult to make. Okay, you go to the underside of glass, so to speak, the underside. That would be the underside here where the condensation takes place, right? And then, you know, you deposit a mirror effectively. Okay, so it is a silver nano layer sandwiched between two chromium layers. The first one plays the role of, you know, helps the adhesion, and the other one protects against oxidation, right? And with the PDMS on top, you're pretty much done, all right? And this emitter, if you measure its emission, it looks like this. It's extremely high in the atmospheric window. It's about over 90.9, the emissivity. And again, the absorptivity would also be high in this wavelength, but there's nothing to absorb from the atmosphere because that is a transparent window of the atmosphere. That is the secret, all right? So, and that works. It's pretty simple to do and works very well. But the story is a lot more complicated, because then I'll tell you why you need the radiation shield. Because the radiation, okay, this window works in the direction normal to the surface, right? But radiation has an angular dependence. So, you know, this high emissivity of the mirror works in the normal direction, but not when the angles are very small. So you have to protect the emitter from those effects, all right? And of course, radiation is not the only story here. I mean, we are all in heat transfer, and we realize that you have other effects. So if this were to operate effectively, you would have Q-dew, which is basically the heat released during dewing, because you want to collect the water at the bottom of this device, right? And we want to basically maximize this. We maximize this with the cooling that I discussed before, radiative cooling to deep space. But there are negative effects. That is the radiation of the sun that really hits your device. And then there's atmospheric radiation at other angles, right? So it's not only the vertical direction that we'll consider, but it comes from everywhere, right? And then, of course, there are convective effects, and you have to optimize this by taking into account all these effects. That is why one needs the radiation field, if nothing else, that I show here. And this radiation field, of course, should block the low angle radiation, okay? And the direct all the sun radiation that falls on your selective emitter through this mirror effect, reflect it away, and also if it reflects on the sides here, is to direct everything toward the theta equals 0 angle. So it is a rather intricate, but for us heat transfer, let's say, connoisseurs, very doable problem in designing this, this shield. I'm not going to give any details, but we've done this, of course. And you see the tremendous effect that this shield can have when you look at the temperature of a sample here, minus the ambient temperature, without a shield, and with shield at different angles. One, in the study, can optimize the angles. We found out that 30 degrees is a very good angle, and you see the tremendous effect in the cooling that the shield has when it is appropriately optimized. You can see this in terms of the sample temperature. You can see that also in terms of the dew temperature, because it does help to bring the sample throughout the day. This is during the day, from a specific day, warm day in Zurich in August, okay, from the morning until noon, significantly below the dew zone. And then during that time, of course, with the sun shining, you still collect water at the bottom because of the low temperature of the selective emitter. And you see here the control without any shield, not a good shield, and then you see the optimal shield in terms of water collection as a function of relative humidities in the atmosphere, and the effect is really, really significant. So very, very important component in the device. Sometimes people tend to focus on the selective emitter, and the shield is secondary. To me, I think this is in this study at least, this was the most interesting aspect. And then, of course, you have the condensation. We're coming back to our main theme today, condensation. And in the back of this, again in the back, at the very end, one can put a superhydrophobic layer. We have developed, with a process that you can see in this paper, a very simple, very easily upscalable approach, combining PTFE, carbon nanofibers, and chlorine dichloride, which is sprayable. You can spray this material on the surface, and has fantastic superhydrophobic behavior. As you can even see from the film here, the droplets, this is in the vertical direction, the droplets are generated, and they have enough by coalescence energy to jump off the surface. So you don't really need to do anything. You just have it there, and the droplets jump off into your tray. All right. So then we'll combine that too, and generate this device, the picture of which I showed you at the very beginning after quite a bit of work. All right. And then the performance is really outstanding, as you can see. We have remarkable max fluxes. First of all, throughout the day, this is 24 hours from here to there. You collect water. Even when you see the spectrum here, when the sun is shining, you have a cold surface collecting water under there, right? Throughout, practically except for this little period, 24 hours, you collect water. And then, depending on the humidity, this is a real life experiment, not a laboratory experiment anymore. It's in the roof of our building, right? And then you can have very high performance. You see some results here for a relative humidity of above 90%. Okay, I want to compare with works of others. It's very difficult because the conditions are always different. All right. But what I compare with is the theoretical limit of this technology, which is the black body, which assumes 100% humidity, no sunlight illumination, and no convective heating. And if I compare with that, the limit is 59 grams per square meter per hour, whereas we're able to reach, arbitrarily, this particular day in August, 52 grams. So therefore, this is a very impressive result. Yeah.
If you can accelerate, and because in about 5 minutes, next session is to start.
Okay, so then the last topic is that of condensation and transparency with respect to anti-fogging. And I will take 5 minutes to basically show you the salient features of this. The problem is, of course, on spectacles that you have deposition, condensation in terms of small droplets because of temperature changes or increase in humidity. And then, of course, the sunlight is not going straight into our eyes. It is scattered on those droplets. And of course, it comes in a scatter form in our eye, and our brain sees that as fogging, right? So it is a very undesirable effect. And of course, there are some technologies that are meant to combat this effect by making the surface, for example, superhydrophilic, so you have a thin layer instead of having droplets. But those are very limited success and very transient. So we try to use thermodynamics, okay, use the sunlight, okay, to again generate, to avoid this process by heating the transparent surface, heating while maintaining transparency. Because if you paint it black, you will absorb the visible. We don't want to absorb the visible. We want to absorb, of course, in the infrared. So the trick here is to have transparent surfaces absorbing only in the infrared, elevating their temperatures naturally, you know, without any Joule heat and anything like that. And in that respect, then ameliorating condensation. I'm going to skip the way we did it. We had a way we used the plasmonic effect. Unfortunately, I have no time to discuss this. And then this is the performance of our latest generation surfaces, where you see that if you look at the transmissivity of the surfaces is very high. They don't absorb in the visible range, and they absorb much better throughout the entire infrared, where the majority, 50%, I would say, of the energy of the sunlight resides. And I'm going to close with a little film showing you the effectiveness of these surfaces. This is a student of mine who a few days ago, tried our surfaces on in Davos. All right, the temperature that you see here, the humidity of only 46%. And then, of course, illumination was not very good. We didn't have that much light. It's, one sun would be 1,000 watts per square meter. This is 2012 square meters. And then, as you can see from this film, which we dedicate to the pandemic, so to speak, that we have to wear masks, all of us, he exhales strongly on the glasses. Okay, and you see both surfaces are transparent. This surface is basically transparent. You lose very little visibility. And when he exhales, when you have a little bit of steam appearing, it disappears immediately because of the heat effect. And then you have maintenance of transparency and no fog formation, and no loss of visibility, of course. So with that, I'm concluding my talk. I'd like to thank you for your attention, and above all, I'd like to thank my collaborators over the year that are really real heroes behind this work. So thank you very much.
Thank you, Dimos, for a wonderful lecture across 3 different problems, all related to condensation, but other things are mixed up in that. So probably one question we can entertain, because it's already late. So maybe one question.
Actually, right now there are no questions, but we can just wait for 1 minute. So there will be a lag between the.
Okay.
Yeah.
Okay. So let me ask you a question, Dimos.
Yeah.
Does it essentially mean that when we are using boiling or evaporation and condensation, we have to use different kind of hydrophobic surfaces?
Well, I don't know about boiling. I mean, the issue the general answer is yes. You have to basically design and tailor, your hydrophobicity to what you want. All right. Robustness is a common thing that they have to have. But as you see, there's the one extreme of film, the other extreme of not touching at all. So effectively, you have to find a happy medium for your application, so to speak. There is not a silver bullet that one thing will kill everything. And that's correct. Yeah.
Okay. If there are no further questions, let us give a big hand to Professor Dimos Poulikakos for a wonderful lecture. And we will remember this wonderful lecture as the first Professor Arcot Ramachandran Endowment lecture. And thank you very much for being with us and enriching our conference.
Thank you very much for the invitation. It's been a pleasure, and I wish you a great conference.
Thank you.
Bye-bye.
Bye.
Thank you, Professor Poulikakos. Thank you, Professor Das.
You want to send me you will send me then the...
Yeah, yes, sir. As soon as we get it, we'll forward.
Thank you very much. Bye-bye.
Thank you.